me. Um, it would have been nicer to visit Mohali in person, but hopefully sometime in future. Um, so please feel free to stop me or interrupt me whenever you have any questions or so. Um, Again, the abstract and overall being election season, it's a bit like election promises. There are a lot of things are promised in the abstract, but it doesn't, matter how much I cover. But I would be more happy that even if I cover less, but it's more followable. So please do interrupt me. Anyway, let's see where we go. Okay, so let's get some very bare minimal basics. So the main object of study here was what is called the Rademacher space. It's just a name is somewhat okay. I mean, all of you would have seen the space for sure, but not everybody knows it's also called Rademacher space. Even I didn't know until recently. So it is nothing but the product space of two elements. Okay, so you take two elements. I call it plus one minus one. There is a certain convenience to calling it plus one minus one instead of 0 1. Okay, and to the power n, and you put a measure on this. The measure is the uniform measure, which is a probability measure. Okay, it's the uniform measure. I call it mu of omega. But so we will switch between probabilistic notation and analytic notation. So let's also say what does this probabilistically. Probabilistically, the space is nothing but I take x1 to xn IID plus minus 1 symmetric Bernoulli random variables. Okay, and all mu of omega is nothing but you can also say it as I think, let me, yeah, should also be able to write, just a minute. Yeah, so this is also mu of omega. Mu of omega is nothing but the probability xi is equal to omega. Oh, sorry, x is equal to omega, where x is the vector of x1 to xn. Okay, so in some sense it's n IID bits, and then we have the expectation of any function of x. You give me any function from omega n to r. Okay, you can write it as an expectation. So you give me any function from omega n to r, expectation f of x. I can write it either as an inner product with the constant function with respect to mu, and you define it whichever way you like, or just a sum divided by some integral of f with respect to mu. Okay, and now if you give me two functions, I can do the same thing, f and g. Then I sometimes will omit the x for convenience. I'll just write expectation f times g. Okay, and this is nothing but inner product again of f with g, and as you can see, it's again the integral of fg with mu with respect to mu. Okay, so whichever way you write it, it is all the same, but it's good to know that there are different ways of expressing the same thing, because it's sometimes quite nice. Okay, or helps to go whichever one you're convenient, you can take it. Now let me introduce the key objects of study. And what is the key thing is that what are the Fourier-Walsh coefficients? So I have to first, I'll define what is the Fourier basis here. Give me any subset of n. So n is, this is nothing but, to me this is 1 up to n, the set. Okay. 1 minute, so switching between something. Okay, so take any subset. So define xs of omega to be all product over omega i's, all the coordinates in s. Okay, and for the empty set, I set it to be 1. Okay, the product over empty set is 1. And now one thing to note is that if I take the expectation here, and the expectation here, because of independence, each xi is independent, so it becomes nothing but product of expectations. And then this is, unless S is empty, this is actually 0. If I say S is empty set, this is 1, else it is 0. Okay, so this is what we have. And now by independence, okay, this is by independence. And then the next thing, is that if I take two S and S prime subset of N, and I take the product of chi S with chi S prime, again the same logic, you can easily write it down and you will get that unless S is equal to S prime, this is 0. Okay, if S is equal to S prime, it's 1. If S is not equal to S prime, this is 0. And this is the inner product also, right, by our notation. And the reasoning is very simple. If S is not S prime, there are at least one bit I naught, which occurs only once. It is either in S or in S prime. It's not there in both. There is one I naught which is present in one, not in the other. And for that, it will be 0. And by independence, again, you can deduce this. Okay, so this is a very, very trivial observation, almost like a first course in probability, even in the first or second week, once one introduces independence of random variables, this is a computation one can ask anybody to do. Okay. And now, what do we observe then is that chi S are orthonormal. Okay, chi S is orthonormal. Okay, because the expectation here is also the inner product. It's orthonormal and there are 2 and many of them. Okay, for every S subset of N, there is 1. So there are 2 and many. So essentially chi S form a basis. Okay, so chi S form a basis. So what can we do? Here is this thing. F of omega can be written as a sum over all subsets of N. Expectation f of x chi S of x times chi S of omega. So any function f of omega, you can write it as some constant. This is a constant, expectation, times chi S of omega. So indeed, if f of omega is equal to some constant times chi S of omega, sum, the orthonormality of chi S implies that the constant has to be this. Okay, there is no other reason for the constant to be anything else. The constant will just be this. Okay, so this is the point. So this is all the constant will be. Okay, so, and now what do we have? I call these constants as the Fourier-Walsh coefficients. F hat of S is nothing but expectation of F times chi of S. This is called the Fourier-Walsh coefficients. The energy spectrum indexed by K, so I will have here, this is K equal 0 to N. Okay, so if indexed by K is F hat of S square, okay, over all subsets of size K. Okay, this is the kth level energy spectrum. And what is the connection to probability? Can these coefficients be interpreted also in more probabilistic terms? Very simply, of course, F hat of empty set is nothing but expectation F of X. Okay, and now variance of F, which is nothing but expectation of F minus expectation whole square. If you just use the orthonormality, it's nothing but what you get from Poincare's formula. This follows from orthonormality. Okay, so you can use orthonormality here, and all you are doing is that in the entire expansion, the first term empty set is expectation. You take it to this side and square it up. So if you square up by orthonormality, you get sum of squares. Okay, and this is in some sense nothing but also Poincare's formula. Okay, so the energy spectrum, when you sum it up, is the variance. Okay, sum of all the energies is variance, and then expectation is F hat of phi. Okay, so quite a basic this thing. So let's look at a couple of quick examples. So first, very simple example is what is called a dictator. We will see complicated examples as we go along. So the very simple example is a dictator. What does a dictator mean is that essentially only the first bit is important. Okay, opinion of the first person alone matters. So, if the first bit is +1, that's +1, else -1. Okay, and in this case, it's very simple. F is chi1, so there is only, in the entire expansion, there is only one term. And the other extreme is what is the parity. F of omega is the product of all. Okay, it's the product of all omega i's. And of course, this is nothing but chi n of omega. So, F itself is equal to a Fourier basis, one element of the Fourier basis. Okay, so it's easy to write out the Fourier coefficients here, Fourier-Walsh coefficients. And a slightly interesting function is majority. F of omega is nothing but sine of the sum of omega i's. So it is an indicator. Okay, if sum is positive, it's +1, sum is negative, it is -1, I take n to be odd so that the sum cannot be 0. Okay, this is the majority bit. Okay, this is called the majority function. And so this is some useful things. We will see more as we go along. Okay, so the key point already you can see for majority, it's not easy to compute the Fourier coefficients. It is not always easy, and the challenge is always how do we compute Fourier coefficients. Okay, and we will see later techniques. This talk is going to be about techniques of how to compute Fourier-Walsh coefficients. Okay, remember again, these are the Fourier-Walsh coefficients. Give me a function f times chi s. Okay, and this is the expansion, the orthonormal or the Fourier series expansion. Two things to keep in mind. Okay, so this is what Jean Bourgain said. It's a general philosophy. It's a common thing in a harmonic analysis. And from the little harmonic analysis I know, that if f is a function of a very high, it's a very highly complex function f, then the support of the Fourier transform of f has to be spread out. Okay, the Fourier transform of f has to be spread out. And this is what, I mean, in various ideas, harmonic analysis, one of the powerful way of using harmonic analysis is somehow to understand that for complex functions, the Fourier transform is spread out. Now we know what is the Fourier coefficients for functions of bits, and we want to understand how is it spread out. What can we say? Okay, so the first people to actually introduce harmonic analysis or this Fourier-Walsh coefficients were Kahn, Kalai and Linial in 1988. It was actually a computer science conference or a journal paper, Foundations of Computer Science, that is for Fox. And here is the thing. One of the first things they rediscovered is, give me f, I introduce what is called the discrete gradient. What do I do for a kth discrete gradient in k at coordinate k is I replace wk by minus wk. Okay, remember it's plus and minus 1, so I just swap it. I just invert it. Okay, if it's +1, it's -1. If it's -1, +1. That's a discrete gradient. And simply by linearity, if you compute the Fourier coefficients of delta k of f, okay, if you compute the Fourier coefficients of the kth derivative of f, I'll just call it the derivative, the kth derivative of f, then it's very easy to see if k belongs to s, then it's 2 times f hat of s, else it is 0. So this is just linearity. Write out the expansion for f, write out the expansion here. Whenever k belongs to s, things don't cancel out. You get a 2 times f hat. If k does not belong, things cancel out on both sides. Okay. So this is the simple thing. And now, here is a very easy observation. Use Poincare again for delta k f whole square, k equal 1 to n. Okay. Now, each of them is equal to this. Okay, so again, if I write out by my Poincare's formula, this is 4. Some, the 2 becomes 4. You get a k equal 1 to n. Sum of all s such that k belongs to s. So this is sum over all s, f hat of s square. Okay, so I sum over all f hat of s square, okay, such that k belongs to s. And very easily rearranging, you rearrange it. Right? If you rearrange it, I can write it as sum over S non-empty and S non-empty, a cardinality of S times f hat of S square. And what is the very trivial observation? Drop this term. Drop the cardinality term. You get a greater than or equal to 4 times f hat of S square, which we know is the variance. This is again Poincare's, right? This is also Poincare's formula. Okay, so this is the very simple observation. The one proof I'll give in detail. The rest all I will be glossing over much faster. I'll be giving only ideas, but the basic idea is always this. Okay, the easiest thing is always to use Poincares, and then you write out, and then you try to analyze the the coefficients with different coefficients, sometimes some rearrangement. And this immediately you get what is called the Poincare inequality. Variance is less than 1/4 times the expected gradient. Okay, so you can also rewrite it also for people who are more familiar with Poincare inequality. This is also the L2 norm. Okay, square of the norm, right? So because the expectation is an inner product, there is an inner product of del k with itself, so it's del k f square as well. Okay, so and 1/4 or some constant. Okay, yeah. And here is a special case that will be of interest for us is when f is in 0, 1. When f is in 0, 1, then the derivative is in -1, 0 or 1. Okay, trivially it is in one of these cases. So which means that the modulus of the derivative is also same as the modulus square trivially, and it is also the indicator whether if you change the kth bit, do you change? That is, I take f of omega, I change the kth bit, I call it omega hat k, okay, where the kth alone is changed. Are these two unequal? That's the gradient. And it's equal to the L1 and the L2 norms are the same here. Okay, that's the main thing here. And L1 and L2 norm are same. And then Ik of f, what is called the influence, is nothing but expectation of the L1 norm, which is also equal to L2 norm because of this. And Poincare inequality tells us that the variance is, this is what is the Poincare inequality when f belongs to 0, 1. So this is because f belongs to 0, 1. Otherwise, it's a L2 norm, not L1 norm. I go from L2 to L1 because it's in 0, 1. Okay. So this is what is helping me. And a trivial corollary, there exists a case such that Ik of f is greater than some constant times variance n. Okay. So that's a trivial corollary. You know, the variance is less than this. So if you take the max here, replace it by the max. So 1/4 max Ik of f. Okay, replace it by the max and then you get this. Okay. So this is what we have. Okay. So Kahn, Kalai, Linial, what did they prove? I'm not going to give, the proof is beyond this to say here. The thing was, it was a conjecture by Ben, Orr and Linial. Kahn, Kalai and Linial showed that there exists a k such that Ik of f is greater than constant times variance by n, the trivial, but there is always a log n also. And this is tight. There are examples where you cannot beat this at all. You cannot go beyond log n by n. So this is what Kahn, Kalai, Linial proved. Okay. They used the hypercontractivity due to Bonamy and Beckner. These are all fairly analytical tools. Okay. And
could you please recall what is Ik?
Ik
okay.
is the L1 expected L1 norm of the gradient. Okay. Yeah.
Thanks.
So all they show is that there is one direction where the gradient expected, the norm of the gradient is larger than what you expect on an average. The average is like constant by n, variance times n. Think of variance as a constant. Okay, this is something non-zero. Okay, doesn't go to 1 or 0. So then all they say is that you have some direction in which it's much larger than the average. Okay, this was conjectured by Ben, Orr and Linial. They used hypercontractivity, harmonic analysis, and they made this claim called the new connections with harmonic analysis are very promising, they wrote. One of the most severe understatements, if you could call it, given that what happened after this paper, how much work it triggered, and it's still, important one. So since then, there have been many developments in, in 90s, there were many developments. There was one due to Friedgut and Kalai, then Bourgain, Kahn, Kalai, Kastner and Linial. These are called the BKKL. They generalized KKL, okay, and they essentially proved KKL for product spaces. That is, they proved KKL for arbitrary product spaces, not just Rademacher space. Okay, instead of product spaces of two element sets, they proved it for arbitrary. And Friedgut Kalai proved something, and there were a good number of inequalities by Talleyrand, finitely many. Okay, proved a lot, but okay, still finite. Okay, so this is something, and to point out that this direction of research is very, very promising. Here is a good exercise for some fairly analytical. If there are students who are not aware of Banach space, it's okay. The rest of the talk, it doesn't matter. I'm going to just briefly touch upon this. Can you prove a Poincare inequality if the function takes values in a Banach space? Does it hold, a Poincare inequality hold for Banach space valued functions? Okay, you still have a Rademacher space on this side, but the values are in a Banach space B. Is it true? If you had a Hilbert space, you could use the inner product structure and carry out the above arguments. You can try this. But if it is a Banach space, it's not always true. It is true only if the Banach space has whatever Rademacher space type 2. I'm not going to say. If there is time at the end, you can ask me. I will tell you. And recently, it was just proved last year in a 13-page paper by Van Andel, Ivanishvili, and Wahlberg. It's a 40-year-old conjecture in Banach space theory. Okay, they settled this. It's a very nice proof. Referred to Pata Ivanishvili's blog. The blog is exclusively devoted to analysis of Rademacher space. Okay, it's a very nice blog. In fact, you can find idea of proof of this as well. This is the key part of their proof. The proof about n-flow and Rademacher is different. This is the key part. Okay, so let's move on. Any questions, anything, please, if anything, just interrupt me and I'll be happy to answer. Okay. So then that's 1988. So as I said, I will skip over a lot of developments and move on to 1999. Okay. So what happened is Benjamini, Kalai, and Schramm were interested in the following question. What is the question? Suppose you give me a sequence of bits. I resample each of them with probability epsilon. What do I mean by resampling? I toss a coin whose heads probability is epsilon for each I independently. If I get a heads, I replace Wi by xi prime, where xi prime is IID plus minus 1. Okay, so x1 to xn, x1 prime to xn prime, all are IID plus minus 1. Okay, and what do? You give me a sequence of bits. I toss a coin. Okay, I toss a coin. If it is heads, I replace it by a random bit. Okay, I replace, and I do it independently for each one. I replace each one by a random bit. I do the replacement with probability epsilon. I don't do it always. Okay, I don't always replace them. I replace them only with probability epsilon. So I call this new one as omega epsilon. Okay, the noisy version of omega is omega epsilon. Okay, that is, or the resampled bits. Remember, some of them will be equal. Some omega epsilon I will be equal to omega of I. It is quite possible that omega epsilon I at some coordinates is equal, because maybe your coin came tails, you didn't resample. Okay, and now onwards I'll assume f is Boolean. Okay, I'll assume f is Boolean itself now onwards for simplicity. There are some things which are okay, you can do it for non-Boolean functions, but it's a good assumption for us. The question Benjamini, Kalai, Schramm asked is f of x and f of x epsilon independent. That is, x itself is IID. You replace some of them. Are they independent? Okay, this is what they asked. So this is the question they asked. I mean, there are various reasons why would you ask such a question. So let's make it more clear. X and x epsilon have the same distribution. Okay, the probability of x is same as probability of x epsilon. This does not change. Okay, because you are replacing, if at all you replace by another xi prime which has the same distribution. Okay, So the probability is not changing. Fnx so has the same distribution of Fn x epsilon. So because x and x epsilon are the same. So sorry, there is no Fn here. This is just F. Okay, f of x has same distribution of f of x epsilon. Okay, but if epsilon is less than 1, x and x epsilon are not independent. If epsilon is equal to 1, you are replacing every xi by xi prime, they become independent. But if these two are not, if epsilon is smaller than 1, this is not independent. Okay, this is a key point. So again, remember, this is what is noise. And noise means that for us, I'm replacing some bits by an independent bit. I'm taking in some bits, replacing it by an IID bit. Okay, that is just IID plus minus 1 with probability half. Okay, so I replace some of them. Which ones do I replace? I do it randomly by tossing a coin. And this is called the noisy version. Okay.
So these xi primes are fixed.
Yeah, xi primes are fixed. Okay.
Okay.
So, I mean, you can, I mean, it's independent, so it doesn't matter. Okay. So yeah, you can a priori either for fix one or only whenever you need I, you choose xi prime. Okay. So you can do either way, it doesn't matter. But for simplicity, maybe take all of them first itself. Somebody has given you everything, entire collection. And then you decide first you take x1 to x1 is x. X is nothing but x1 to xn. Okay. But x epsilon for me is x1 epsilon dot 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 xn epsilon. Where with probability epsilon, x1 epsilon will be xn prime, or else it will be xi itself. Okay. So you decide randomly whether x epsilon should have xi or xi prime. Okay. Thanks. Okay. So the motivation of Benjamini, Kalai, Schramm was what was a very famous conjecture and is behind two Fields medals, is conformal invariance of percolation models. So this was the motivation to study this. That's a bit hard to describe here, but it had a lot of other motivations. In sense, in theoretical computer science, people were wondering that if some number of bits were changed, for example, you take an election and you are interested in the majority, okay, but if you had some counting in error, there was some error in counting or some votes were missing, some bits are missing. So you think of it as noise. How does it affect the output? How do noisy bits affect the output? Okay. And then in statistical physics, they were interested in dynamical percolation models and so on. In networks, people are interested in dynamical random networks. So you can think noise is introducing some dynamics because noise is changing the input. Okay, you are changing the input. So what happens to the network when you change the input? Okay, so these questions were asked by various people and noise sensitivity provided a framework. Let us formalize the question of noise sensitivity. Okay, so this is the formal definition. A sequence of functions is said to be noise sensitive. A sequence of functions is noise sensitive if for all epsilon greater than 0, covariance fn of x with fn of x epsilon, this is the definition of covariance. If for those, so covariance of fnx with fn of x epsilon is nothing but expectation of the product minus product of expectations. Okay, if this converges to 0. So if fn and fn x epsilon were independent, this will be equal to 0. Okay, this is equal to 0. But we are saying that fn becomes asymptotically independent of fn x epsilon becomes asymptotically independent of fnx. These two are asymptotically independent is the claim. Okay, asymptotically independent is the claim. Okay, and it is equivalent to also say the given x, the probability fn x epsilon is equal to 1 given x, okay, is same as probability fn x epsilon is equal to 1 asymptotically. These two that is telling you X value, I mean the configuration at X does not, I mean it really dramatically, you get nothing about Fn X epsilon. Okay, so this is the point. Okay, so two minor points. I don't need to check this for all epsilon. If it is true for some epsilon, it will be true for all epsilon. You can check this. This is not very hard. If it's true for some epsilon, it will be, in fact, we will see a proof of this already. Okay. And then if you give me a sequence of functions, which is asymptotically a constant, the function is probability of Fn equal to 1 is going to either 0 or 1. It means asymptotically Fn is 0 or 1. Okay, it is almost surely a constant. A constant is always independent of itself, so the covariance goes to 0 trivially. Okay, if Fn's are degenerate, trivially it's noise sensitive. So degeneracy is if you give me a degenerate set of sequence of functions, noise sensitivity is trivial, it's uninteresting. Okay, so the interesting thing is non-degenerate functions which are noise sensitive. Okay, so I will again pause a moment, and it's an important thing for the rest of the talk. That this, we have this in terms of an inner product. Okay, so again to write this is Fn, right, omega Fn omega epsilon in mu and times just Fn. Okay, because both of them have the same distribution. Fn of x has the same distribution as Fn of x epsilon. You can verify these two expectations are the same. Okay, so I wrote it with x epsilon, but I put a x, so it's nothing but Fn times the inner product minus the square. Okay. Okay, so Bourgain's philosophy, we will now see what Bourgain's philosophy in action. So here is an operator called the noise operator. Nothing fancy. It's T epsilon f of omega. F is a function, remember f is from omega 1 to 0, 1. Okay, T epsilon f of omega is nothing but the expectation f of omega epsilon given omega. Okay, this is the part I'm going to be a bit hand wavy, but this is actually a probability exercise again, very basic probability. You have to write down that with probability 1 minus epsilon, omega I is omega I epsilon, else they are independent. Okay, so if any coordinate omega I is actually replaced, if in any coordinate omega I is replaced, okay, omega I is replaced, it becomes independent, then that coordinate will become 0 and everything becomes 0. And so it means that all the coordinates omega epsilon, in all coordinates s, you use linearity, and all coordinates s, omega I should be omega I epsilon. That probability is 1 minus epsilon. That probability is 1 minus epsilon to the power s. Okay, cardinality of s. So the noise operator, T epsilon f, the Fourier expansion is also very nice. It's the same f hat with this extra prefactor. Okay, very nice prefactor, very easy prefactor. And now expectation of f of x times f of x epsilon can be rewritten. This is a simple conditional probability formula. This is, I mean, so far might be maybe a little quick at times, but if you sit down and write for yourself, okay, you can see all of them. By the way, I forgot to say one thing. I don't know how many noticed. I put up the talk slides on the chat as a file. I don't know if people are able to access it. Sorry about it. I forgot. Okay. So you can check something if you need, or even later. So expectation f of x times, you can write this as expectation f of x epsilon given x. Okay. And now this is nothing but the noise operator. So this is the noise operator, same by the definition. This is definition of noise operator. And then use orthonormality. This is orthonormality. Okay, I know the Fourier expansion for this. It just has an extra prefactor, and this is f of x has no prefactor. So if you put it, you get this. Okay, and now when you are taking the covariance, you subtract the s equal to empty term. So remove the s equal to empty term, bring it to this side. It's the covariance. Okay, and you get s non-empty. This. Exactly like the variance formula. Remember, we had a formula for variance using Poincare. It's exactly the same formula, except this prefactor. Now, very, very nice. Okay. This is really nice. So here is a little argument I'm going to gloss over. It's a bit of a small analysis argument. F is in 0, 1. So the sum of f hat of s square is variance of f, which is at most 1 over 4. Okay, so you can bound it even by 1, but it's at most 1 over 4. Okay, because it's of the form of p into 1 minus p. So it's at most 1 over 4. So if I want for a sequence fnx epsilon to go to 0 as n goes to infinity, what has to happen is that for any fixed, because this will be summable, right? This is always bounded. You can write here. This is less than s non-empty f hat of s whole square. Okay, so this is always bounded. So the terms for s very large, you can control. When s is very large, this will take care of things. You can control it easily. Okay, and so you have to only worry about when s is small. And so covariance converges to 0 if and only if energy at every finite level converges to 0 as n goes to infinity. So every finite energy has to go to 0. So that is, energy spectrum is concentrated on high frequencies because low frequency energy spectrum vanishes. So when I say low frequency, it means k is small. Okay, so your k is fixed. So every fixed k, energy spectrum vanishes. Remember, n is going to infinity. So the energy spectrum can be from 1 to n. There are n levels for the energy spectrum. Okay, Ek has 1 to n. I'm saying all the fixed energy spectrum vanishes. Okay. So this is Bourgain's philosophy that somehow a complex function, the energy spectrum should be well spread out. And here it's saying that it cannot be concentrated on low spectrum. Okay, it has to be completely on high enough spectrum. And so you have this very easy criteria for noise sensitivity, that a function is noise sensitive if and only if all the finite energy spectrum vanish. Okay, so it's noise sensitive if and only if all the finite energy spectrum vanishes. Okay, so here are some easy examples. Again, let's look back at our easy examples. Dictator, of course not noise sensitive, because it's concentrated on the first energy spectrum. Okay, it's completely concentrated on the first one. So you can write here Ek. So E1 of f is equal to 1. Okay, and this is the other end is the parity. It's concentrated on completely the largest energy spectrum. Okay, chi n. So En of f is equal to 1. Okay, so this one is E1 of f is 1 and this one is En of f is 1. So these are the two ends of things, and then so one is not noise sensitive, other is trivially noise sensitive. Majority is actually not noise sensitive, but needs some argument via central limit theorem and so on. Okay, I'm not saying for majority. Okay, so here is a condition which is not very easy at all. This is not, you can check in some simple cases, but you have to compute the Fourier spectrum. Okay, I have not told you how to compute the energy spectrum, but I'm telling you that if you can show that high energy spectrum vanish, the function only low energy spectrum vanishes, it's noise sensitive. How do you check noise sensitivity now? You have to compute the low energy spectrum. Is there some way of computing low energy spectrum? Okay. 1988, 1999, let's get to 2010. Okay, it's an interesting coincidence. It's all 11 years apart. And now it's 2021. Okay, So it's just a coincidence. So then 2010, Schramm and Steif came up with this. Well, it's published in 2010, so a few years before. Schramm and Steif came up with this beautiful idea. Okay, it's sort of magical. Is what? Let J be a random set. Let J be a random stopping set. What do I mean by a random stopping set? It's a subset of N. It is random. It's not fixed. It's random. It depends on Xi's. You are given me Xi. Remember, I'll write here. X is X1 to Xn, IID bits. Okay. So give me some IID bits. I determine a random stopping set J. What does it mean? It heuristically means that the value of Xi inside J should be independent of that outside. If you tell me J and the value of Xi inside J, it should tell me nothing about values of Xi outside. Okay, this is a very, very crude definition. It's not correct, but it's intuitively, this is to think about it, that telling me inside the value of the bits inside the random stopping set should not tell me anything outside. Okay, and J, I say J determines F. If f of X is f of X restricted to J. That is, if you tell me all the values of the bits inside J, I know f of X. I don't need to know the values outside J, and J is random, and outside J things are still random. Okay. So this is the point of random stopping set. Okay, that is you check bit by bit randomly. You check some random set of bits. I tell you all the values of Xi in this random set of bits. Okay, and based upon this, you decide to say, okay, it's enough or not enough. Okay, and you don't look outside this at all. Okay, you know f is 0 or 1 by just looking inside the bits inside J. And now revealment probability is nothing but the maximum over all I belongs to J. Okay, the maximum over all I belongs to J. Okay, this is the probability of revealment of a bit. A bit is revealed by the random stopping set is if the bit belongs to the random stopping set J. And Schramm and Steif came up with this remarkable inequality, which said that the kth level energy spectrum, remember again, this is nothing but S is equal to K, F hat of S square. Okay, the kth level energy spectrum is upper bounded by K times the revealment probability times expectation of F square. This is not a problem. You know, F takes value 0 or 1, so this is at most 0 or 1. Okay, in fact, this inequality is true even for real valued functions, as I've said here. But for our case, it's okay. And now the magical thing here is this. Previously, people thought about this very analytically, and Schramm and Steif suddenly brought in a whole new randomness into the business. They said you can estimate the Fourier coefficients or the Fourier spectrum by coming up with a smart algorithm which will reveal very small set of bits. So make revealment probability very small, you can control the energy spectrum. This is what Schramm and Steif did.
Yogesh,
yeah.
I missed something. So this J need not be unique for a given F.
No, it need not be given unique at all. That's the point. That it's how smart you are in coming up with the algorithm that will change. You know,
but your revealment probability is
will change.
Yeah. Okay.
So that is, I can come up with one algorithm. Neeraja can come up with a different algorithm. Okay. So you know, and the point is that whoever comes up with the better one, you get a better estimate. Okay, and there is no general procedure to say. I mean, Schramm and Steif have some indication of an algorithm which should be the optimal one, but nobody has yet proven it's optimal or managed to understand this algorithm very well mathematically. Okay. There is some very canonical algorithm one can think of, but it's hard to estimate things using that. Okay. So this is precisely
this inequality is for those sets which will determine F. right?
Those algorithm, those stopping sets J. So J is like a stopping set. I also use the word algorithm because, the stopping set, you are revealing bits one by one. Okay, so you sort of think also like you are revealing bits. So those stopping sets that determine this thing, I should say here.
So will they always exist?
Trivially take the full set.
Of course, yeah.
So if you take the full set, you get back,
sure.
the trivial point. Okay, J is stopping set determining.
Yeah.
Okay, so there exists one, so there exists a minimal one also. Because there are finitely many,
of
right?
course, if you take the full one,
yeah.
But then one would like to have a smaller one, I suppose.
Yeah, precisely.
To have a better inequality.
You want something that for Fn, you want something that goes to 0 actually. Okay, right? In our case, we want the energy spectrum to vanish for small k. So which means for every fixed k, if you give me a sequence of Fn, I want to come up with a sequence of Jn such that this goes to 0. Okay.
So does it also has applications in counting these, integer lattice points or something? I don't know. It looks somehow maybe, I don't know.
I've not seen, but I'm not sure yet.
Okay.
Okay. The point of this inequality, again, like what many of you are curious, is that here is a purely analytical object. People, like all the inequalities I said, Bourgain, Talagrand, everybody, they proved analytical inequalities, okay, with something. But what Schramm and Steif came up with something completely random and something which gave you a lot of freedom. You come up with something, algorithm, you could improve. So this was fascinating, okay. And here are two consequences, because one consequence I won't say, but it's not too hard, is you can improve the Poincare inequality. Okay, one consequence is you can improve the Poincare inequality. Okay, there are analytic improvements like log Sobolev and so on and analysis, but Schramm-Steif gave a different direction of improvement, which is now in terms of an algorithm. Okay, previously we had a factor 1/4. Here I now have something which is, can potentially go to 0 also.
So just one more point I would like.
Yeah.
So, but then this constant depends on the function f, right?
This one, yes, it depends on the function f. So it could be in many cases. So if you forget, the constant could be much smaller than the previous factor was 1/4 independent of the function.
Yeah.
This one, maybe if you give me a sequence of Fn, this constant should potentially be going to 0 also. Whereas the previous Poincare inequality, you don't get variance going to 0 by this.
Perhaps that is what one is looking for.
You want to know when can Poincare inequality be beaten. It's a very important thing in probability increasingly. There is an entire monograph and studies. When is Poincare inequality improved? There are very classical things like log Sobolev inequality, modified log Sobolev inequality, and so on. But Schramm-Steif is a completely different direction to improve Poincare inequality. Okay, it's a completely different direction in which they improve Poincare inequality. And the next thing, which is actually easy, which is a very simple exercise, because you see, we wrote down the covariance in this form. 1 minus epsilon to the k times the energy of f. This is what we had, the formula. And now just substitute the Schramm-Steif inequality and you get this bound. You get this bound now. Okay, very easy bound. And so once you plug in, the definition of noise sensitivity is that this has to go to 0. And Schramm-Steif inequality tells you that if you have a sequence of fn's, if you get me random stopping sets Jn determining fn's, for every fn you find a random stopping set Jn, and delta fn Jn goes to 0 as n goes to infinity, the covariance of fnx not alone for a fixed epsilon will go to 0, but you can also let epsilon go to 0 at a suitable rate. That's it. Okay. So this is what is Schramm-Steif inequality will tell you. I made a mistake here. It is epsilon n faster than this. Okay, epsilon n has to go to 0 faster than this. Okay. Sorry, slower than this. That's the point. Okay. So you can even quantify the epsilon instead of fixed epsilon. You can even take epsilon and going to 0. depending on your algorithm, and let the covariance go to 0. So this gives you a condition now for noise sensitivity. So it tells you a lot of things. If I want to show something is noise sensitive, it tells me all you have to do is to come up with a sequence of random stopping sets determining my function fn such that the revealment probability vanishes. Okay, so this is the main thing which motivated Schramm and Steif, but it's a remarkable result in itself that this very analytical thing, they are bounded it by something using randomized algorithm. And to me, it's a very beautiful merger of probability, some intuition from harmonic analysis, and then something from theoretical computer science. Okay, I think it's, in some sense, it's a bit magical to me always. I see this. Whenever I've said this, I've used the word magical. Some people, if they're listening again, they might be bored. The reason is it's hard to guess why they came up with it to me, even when I see the proof. Okay, I'm a bit short of time. I won't tell much about the proof or anything. The proof, in one line, the proof is, there are a lot of consequences of this. You can analyze things like exceptional times, Hausdorff dimension of, things, and various other things which we cannot discuss here. Forget the consequences. Proof is, you use this simple identity, expectation f times t can be written in this way, conditional expectation formula, and then use Cauchy-Schwarz. Okay, this is the only inequality actually. In their proof, one inequality is this, and there is one more trivial inequality they get, is that you apply G, you set G to be sum at the kth level, then the energy is nothing but expectation of f times t. If you put this G, you have this, and then you use this and understand the Fourier coefficients of this. The proof is not a lot, 1.5 pages max. Okay, even in their original paper, it is quite nice. But okay, it's hard to give any, I don't get a great intuition into that. And there are extensions to arbitrary random variables, not just plus and minus 1, by O'Donnell, Sachs, Servetio, and Schramm. It's called OSSSS. Okay. So I will give an application. Okay. So again, the point I will reiterate is, this entire business of estimating Fourier coefficients are now coming up with an algorithm. That's it. Give me a function. I want to understand its Fourier coefficients. I'm telling you, Schramm and Steif have told us that give me an algorithm with small revealment probability. That's it. Okay. This is the beautiful heuristic. And now, okay, here is almost one of the trivial applications of Schramm and Steif, I would say. But it was non-trivial in the context in which it is proved. I mean, I would say before that, it was still somewhat non-trivial. So here is a very classical application.
So, sorry.
Yeah, no problem.
So can we analyze that, can we say something that for what kind of functions we can have such J, that sequence tending to 0, something more about those functions, when can we expect?
Yeah. So one thing you can do is following. Suppose, say you have this, right? Mm-hmm. And you have some bounds on upper bounds on sometimes the gradients. You can use it, and you can get a lower bound in terms of variance and something. Mm-hmm. You can derive some lower bounds for what is the smallest possible revealment probability you can have. But it is hard to, I do not know whether there are, you can say that is achieved. There are guesses, there are things, but I don't know if there are a priori you can say very easily that, because it's, I can tell you some algorithm which does something not so good, but it's hard for me to say that nobody can improve what I say. Mm-hmm. At least, I would be very skeptical of making a claim that someone can be not smarter enough to improve my algorithm. But
so if Fn is supported on a smaller set, I don't know.
That is the trivial part.
Yeah.
Okay. But
then the Fourier coefficients. So I'm trying to, since being a harmonic analyst, I'm just trying to relate it with the Fourier coefficient behavior. you know, so.
So if Fn is supported
yeah.
on a small set, it cannot be, I mean, it shouldn't be. The point is we don't want it. Yeah, if it is supported on a small set, trivially it won't be. So that's a reasonable bound to say that, okay, if there is some level K on which it is supported, then trivially you get a bound.
Yeah.
Okay. But often the interesting thing for this algorithm is case where you cannot understand the Fourier coefficients. You try to understand by bounding. If you can directly understand the Fourier coefficients, actually the problem becomes simpler.
Yeah. So it gives you more information about these Fourier coefficients also. I mean,
yeah.
That's nice.
Okay.
Yeah. It's really magical in your words.
Yeah. I mean, one can even read the proof. Some results, once you read a proof, the magic sort of goes down. Okay. But I don't get an intuition even from the proof. And even I saw people describing why one would expect such a result, and nobody has a good explanation for it. And maybe sometime I can ask Steif. Hard to ask Schramm now, but hopefully Steif will have something to say. Okay. So here is an application. So what do? Take a integer lattice, kappa n is the length and n. Okay, I have a box grid, I have a grid of length kappa n and height n. What do? Each edge is open. Whenever it is 1, it's open. Whenever it is -1, it's closed. So LO edges are open, okay, and white edges are closed. And now all we ask is there a crossing? Is there a crossing from left to right in this via open edges? I call this an open crossing. Okay, this is the function. So my function Fn is indicator there is a crossing. My function is that there is a crossing. Okay, so this is the function I have. And Rousseau, Seymour, Welsh in a very famous result in 1980s showed that the crossing function is non-degenerate. That is, the probability of crossing dependent on kappa is between 0 and 1. It does not go to 0, it does not go to 1. It is in some interval bounded away from 0 and 1. Okay. So this is what Rousseau, Seymour, Welsh showed in 1980s, a very famous result called RSW. So this probability of crossing, they said, is non-degenerate. Okay. And the question was, is this noise sensitive? That is, if I change a few edges, if I resample a few edges, maybe this edge, I noise.
Okay.
Yes.
I didn't get. I think you want to be at the critical value, right?
Yeah, my bits are always at probability half. So I always assume my probability of xc equal to 1 is equal to half. Hello, is that okay?
Yeah.
I'm working with the uniform measure for that reason only.
Maybe I missed when you said it. Okay.
I said right at the beginning that I'm taking the IID bits uniform.
No, they are IID.
Uniform also.
But okay.
Yeah. So that's a key point. I've chosen the half for a particular reason to, there is something very specific about half in this model. You can do with other P, but not this application is not the correct one then. Okay. So the half is chosen both for simplicity and also for the application. It worked out very nicely. So Fn is, it's the indicator. You have a crossing. Fn is this indicator. And now my randomized stopping set, I'll just quickly say, I'm not going to give details on this, but the point is the randomized stopping set is choose one vertical line. Look at all the open edges connected to this vertical line. So this is all the blue edges here. Okay. In fact, a little more. I should have done a bit more. I put the wrong thing. So it is all the blue edges connected to all the blue edges that are connected to the blue edges are my randomized stopping set. Okay. So it means that all the edges that are connected to the vertical line are my randomized stopping set. Okay. So if you know all these values at all these blue edges, I know if there is a crossing or not. Okay, because any crossing has to pass through arbitrary vertical line. Any crossing has to cut through the line. Okay, any crossing has to cut through the line, and I'm looking at all the edges, open edges that cut the line. Okay, so I'm being a little quick here. So just if you cut through the line, you explore that edge. So all the blue edges, and you can do some very simple computation to determine this bound. That you get a bound like this, where theta s is the probability. You have an open path of length s, and you can get that this goes to 0, and so this is like 2 by n times this. Okay, so this goes to 0 at half. One can show this. This goes to 0. This is a slightly non-trivial result. It follows from RSW also, and then you get a 1 over n factor. So this will go to 0. So delta fn jn goes to 0. The reason is the line is random. Okay, I've chosen a line very randomly. So it means you give me any edge. The probability it is connected to a random line is very small. It can be connected to a line very close by, but it cannot be connected to a line very far. Okay, so the line is random, that helps. So it is noise sensitive and all that. And essentially what Schramm-Steif does is the moment you have non-degeneracy and this probability of an open path of length n goes to 0, and you have essentially if you have RSW, you get noise sensitivity. That is what Schramm and Steif have done. They have reduced noise sensitivity question to proving a RSW type result. Just non-degeneracy and some probability going to 0. So very, very clean and very neat. It can be applied to wide variety of models. So I've been a little quick here. I don't know, Jyoti, how much time? Maybe I've already exceeded, or if I can take a couple of minutes to.
Sure, you can take, sure.
Okay. So I'll just take a couple of minutes. I mean, and then I can take questions. Okay. I was anyway hoping to spend 5 minutes on the last part to say something about what we did, but it's, I mean, if you have understood Schramm and Steif, which is the bigger inspiration and more generally useful, it's okay even if you don't follow so much of our work. So I'm not going to give so many details here. The key point is that what we are doing is that you take a compact set, you take a Poisson random variable n, you take IID uniform random variables on the compact set, and instead of a vector of a finite length, I have a set of points, random number of random points. This is called a Poisson point process. We have a random number of random points. Okay. And we want to study f of eta. Functions of Poisson process. Eta is a Poisson process. We want to study f of eta. Okay. And this is what we want to study. And what we will do, just 1 minute, the laptop is running out of charge. Sorry. Okay. So what we say is that I'll skip all the details. The key point is there is a equivalent of energy, or there is a equivalent. We don't have always Fourier coefficients explicitly. It's not easy, but energy, there is some, orthonormal expansion. There is a orthonormal, what is called the Wiener-Ito chaos expansion. It's an expansion of f of eta in terms of something, whatever that something is irrelevant. Okay, all that matters is it's as orthonormality. So you have something equivalent. And what we show is essentially we have a analog of Schramm-Steif inequality for this quantity. Okay, so Poincare inequality is classical, and the importance in Poisson process is for a Poisson process, you don't have any of these inequalities, which all use hypercontractivity, and Poisson process does not have good hypercontractivity properties. Okay, so the problem comes in this level, and I won't say anything more in detail. You can again do some percolation application we do in our paper. Okay, so I'll push it off, and interested people can check. Either the paper or I gave a talk a couple of months ago in the Bangalore probability seminar in detail. The slides and video are available online. I can also send you the link. Okay, so let me stop here. There are a whole bunch of things I will, references which are very useful. I'll highly recommend two things. One is Ivanishvili for very, what other things you can do here. Very, very beautiful. Van Handel's book is very nice. And then, all these are surveys. excellent things. There are many interesting things in all of them, different perspectives. Okay, and it's a very active field. I'm just citing 4 papers even from the last 1 year, which all have proven some remarkable results. Okay, so just studying this simple space plus minus 1 to the power n, there seems to be a lot to do. Sorry for the overtime, I'll stop it.
Okay. Thank you for a wonderful talk. So are there any questions?
Is it easy to see why majority